So here we have chapter 4.1, and we're talking about heat engines. So what are heat engines? I'm going to use the definition given from the book. It's any device that absorbs heat and converts part of the energy into work. So how do they work? Well, as looking at figure 4.1, we have a hot reservoir with a temperature. I'm going to call it TH for hot. Then we have the engine. I'm going to do it in blue because it's a little more important. And then we have cold reservoir. Okay, so from the hot reservoir, we get heat, of course. And then into the cold reservoir, we input heat. I'm gonna tell you what this H and C mean in a minute. And then on the right, we have our work, oh, the work that is done by the engine. So what happens? Well, an engine is not perfect. An engine always has to dump some hot temperature, some heat outside. Um, so not all of the heat can become work. This is because whenever we have heat moving from a hot place to a cold place, so we have heat moving from a hot place to a cold place, we have an increase in entropy. That means that this movement causes heat because the entropy increase, and of course entropy cannot just be uh, cannot just be um, de- destruct cannot be erased from the universe. Therefore, we need to dump the some of the heat as much as we can into an even colder reservoir where we are losing some of the heat that we absorbed, but we are getting rid of this entropy that has been created. Um, and of course, this means that not all of the heat can be used for work. If you imagine um, a an engine of a car, which is not exactly an engine, but you get the point, takes and it takes uh, heat from burning of the gases, burning of the um, petrol, fuel, whatever you want to call it, and then it makes it become work or the car moving. However, not all of it has been transformed into energy for the car moving. In fact, some of it becomes heat. In fact, the engine is very hot, and that's why you need to cool it down to make this process um, a little bit better. So, um, well, not to make the process a little better, actually, to make this um, to make not to not make the engine break. So that means that some of the heat then is dispersed into the engine and then it's dispersed into the air. Now, the ratio between the benefit that we're getting or the work and the initial the cost that we had to the cost of the heat that we started from, or QH, which is the heat coming from the hot reservoir, is equals to the efficiency. While QC is instead the heat that goes toward the cold reservoir. So for example, QH is the energy that is created by burning fossil fuel. If we have a car like with engine, with gas, and work is the energy that then becomes the energy that moves the car. While instead, Q cold is instead the energy that goes into heating up the engine, and then of course the environment all around. Okay, and therefore it means that the the energy that is given by burning of the fuel is going to be equals to the work done by the engine on the car, or the energy that is then used to move the car, plus the heat that is then dispersed into the environment around. So, by knowing this, we can look back at this formula we wrote on the left, and we can say that efficiency is equals to, well, if we rewrite this, we get the work is equals to Q hot minus Q cold. So we get that Q hot minus Q cold over Q hot. Or, obviously, we get Q hot over Q hot minus Q cold over Q hot, which is equals to 1 minus the ratio between Q cold minus Q hot. Okay, and we know that the ratio between the heat and the temperature is going to be the same. Sorry, it's going to be higher for colder, the colder reservoir than for the hot reservoir, or at least it has to be equal or greater. So we can rewrite this as Q cold divided by Q hot greater or equal than T cold over T. So oops, I wrote okay, T hot. Now, where does this come from? Well, we know this is true. Actually, we know this is true because of the entropy. In fact, we always have to go back to the initial point and say that the entropy that is then given to the cold reservoir will be the entropy that we get from the hot reservoir. Therefore, the entropy in the hot reservoir decreases while the entropy in the cold reservoir increases. Okay, and now that we know this, we can say that we can plug it in actually in our equation over here. So we have the efficiency is less than or equals to 1 minus T cold over T hot. This is because here we're talking about an equal, but here we're talking about greater than or equal. And then when we substitute something into greater than or equal, then of course the sign on the left, we can be still equal, but it will also want to be less than. We can give it a real value. So for example, we can say that this is 0.5, and therefore the part on the side, on the left, on the right, will have to be 0.4. Okay, so you can say that efficiency is equals to, let's say, 1 minus, and then we use the initial formula, so 0.5. So it goes to 0.5. Then we say that efficiency is less than or equal to 1 minus 0.4, or that efficiency is less than or equals to 0.4. Sorry, 0.6. And as you can see, it makes sense even in our calculations. We have a real life example with two temperatures. You can just plug in inside this equation right here. There's not really much to add to it. And that's pretty much the first chapter. It's pretty simple. The only thing is that it talks about towards the end is the efficiency. The efficiency can be equals to 1. When what? Well, let's look back at this formula that we have right here. Actually, no, let's look at this one right here. Less than or equals to this. Actually, I want to use the real formula, even though, actually, yeah, I think this might be the best one to prove it. So we want then this one to be the smallest values possible, because of course it's 1 minus that, and of course the highest efficiency, the average efficiency is going to be equals to 1. In order to do this, it means that T cold has to be equals to 0, and then T hot has to approach 0. Sorry, or. We have an or here over here. Now, of course, this is not actually achievable because we don't have a infinity temperature or temperature equal to 0. Because of course that would mean that there's no actually any mass, and therefore we have an efficiency that is never going to be equals to 1. We're never going to have a perfectly efficient engine.